In this problem, we're going to calculate based on the temperature distribution. Suppose we had an infrared sensor or camera, and we could see what the temperature distribution was in this object. The object has the dimensions Lx, Ly, and Lz. The goal is to figure out, maybe for instance, how much total energy does this object contain. So recall that total energy is equal to, there could just be, I'm just going to use E because it could be enthalpy or internal energy, equals some energy density times the volume. Here we're going to have V go to a very small incremental volume because we're going to consider this thing as a bunch of little tiny pieces all summed together that gives us the total energy in the system. So the local energy density is equal to the specific heat capacity times density times the temperature at that position in space in that object. As it zooms, as you get smaller and smaller. Recall that the energy we calculate is always relative to some reference temperature energy. And so this becomes then an integral over the entire domain. We just call it omega of E d omega in general for 3 dimensions minus the energy over all of omega of the energy density of the reference d omega. In Cartesian, as we have here, we simply have x is on the interval of 0 to Lx. Oops, that's inclusive of Lx, not exclusive of Lx. Y is on the interval of 0, Ly. And z is on the interval of 0, Lz. So when we just make the substitutions into our equation, we want to calculate the total energy. This could be internal energy, let's say, minus our reference temperature energy, because it's always relative to something else, is equal to 0 to Lx, integral 0, Ly, integral 0 to Lz, c bar rho temperature is a function of x, y, and z, and this becomes dz dy dx minus c bar rho temperature reference, which will be a constant, which then just becomes times Lx, Ly, Lz. So this is how you can calculate total energy, for instance, in a brick or something that you are using as a source of energy in another situation.